All right, everyone, welcome back to Calculus 3. So where we left off last time was I claimed that there was a way to extend Green's theorem to vector fields that were defined over 3 dimensions, or they're defined over R3. So we had 3 components, not just a P and Q, but a P, Q, and R. So what we're going to do is we're going to get to that generalization today, and we're going to see what we can do with it here. Now, I apologize in advance. I accidentally only brought the notes that I wrote on earlier, but I'm just going to write over what I wrote earlier. So I'll try not to go like too fast just because it's already written down here. All right, anyways, so before we could talk about the analog to Green's theorem, which is spoiled right here, it's going to be called Stokes' theorem right here. Let's talk about the positive orientation of a boundary curve. So let's say we have some smooth surface S, and it has a unit normal vector n. So here's a good picture of this. We have these little normal vectors pointing upwards here. The orientation of S induces the positive orientation of the boundary curve, delta S, shown in the figure below. If we walk around the boundary curve in the direction of its orientation with our head pointing in the direction of n, then the surface is always on our left. Now, I don't know if you can see this clearly in the printout, but this is actually like a little person right here, and they're walking in the direction of the curve right here. So they're walking in the direction of the curve, and their body is aligned, and their head is pointing in the direction of this normal vector right here. So as they're walking along, notice that the surface is going to be to their left. So this is going to be considered a positively oriented curve. And remember, we need to keep our orientation in mind, because if we have the wrong orientation, we will be off by a negative sign. All right, with that being said, let's go ahead and get to Stokes' theorem now that we know what that orientation is. Let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve. So kind of like this right here, with positive orientation. Assume that we have a vector field, which now can be over 3 dimensions, P, Q, and R. And it's a vector field whose components have continuous first partial derivatives. So we can compute this. Then Stokes' theorem says that the integral around the boundary of f dot dr is going to be the surface integral of del cross f, which we learned last time was called the curl of f, dotted with the normal vector ds, where n is the unit normal vector determined by the orientation of s. So using the curl, we were able to create a generalization of Green's theorem called Stokes' theorem right here. All right, now one interesting thing that happens here, so usually when I introduce these theorems, there's a case that makes them be 0. In this case, if S is a closed surface, like maybe S is a sphere or an ellipsoid or something that kind of encloses a volume, then if we compute this, we're going to end up getting 0. And why is that? Well, if we use Stokes' theorem here, we don't have a boundary curve for something like a sphere. So if we draw a sphere like this, there's no curve that's kind of at the edge of the sphere. Like there's no edge to the sphere. So there's no boundary to integrate over, meaning that this will end up being 0. Oh, whoops, thank you. Yeah, so there's no edge or boundary curve to the sphere. So we have nothing to integrate over, meaning that this will be 0 right here. So if you ever have a closed surface, then this will automatically end up being 0. So that could be a shortcut that we'll use in the future. All right, so let's go ahead and practice this. So what we're going to do first is we're going to practice finding parameterizations of these boundary curves, and then we're going to use that practice to help us use Stokes' theorem right here, because we need to know what the boundary curve is. All right, so find a parameterization of the boundary curve delta S or ds, or the boundary of S, with positive orientation if, now here's the first situation. S is the part of the surface of the paraboloid, z is 5 minus x squared minus y squared, above the plane z equals 1, with a normal vector pointing upward. So our normal vectors will look something like this to our surface. All right, so remember what we're supposed to do here. So remember, if we're going in the direction of the normal vector, let's say we're a little person that's as tall as this normal vector and we're walking around, our surface will be on the left if we go around this circle in a counterclockwise manner. So in order for this to be positively oriented here, we need to go around the circle counterclockwise. All right, well, we know how to parameterize a circle. Oh, by the way, how do we know that this is a circle? Well, this is where the paraboloid hits the plane z equals 1. So the paraboloid is 5 minus x squared minus y squared, and we set that equal to the plane z equals 1. We add this over here and we subtract 1 over here. We end up with the circle centered at the origin. X squared plus y squared is 4. All right, so we just need to parameterize this curve, and we've parameterized circles millions of times here. So for my x coordinate, I'm going to use 2 cosine of theta. And then for my y coordinate, I'm going to use 2 sine of theta, because this is a circle of radius 2. And then for my z, remember that this is on the plane, z equals 1, right? So the z value is going to be 1. By the way, let me know if I'm writing a little too fast. There's one reason why you don't see a lot of math classes given in PowerPoint. It's because if you don't write the stuff down, you go too fast. So if you see me going too fast and not writing over what I'm writing, just let me know and I can slow it down a bit. All right. So let's do another example here. So S is the part of the surface of another paraboloid, z is x squared plus y squared minus 4, and below the plane, z equals 2, with a normal vector pointing downward. All right, so this time we have a parabola that's opening upwards, but it starts down here at z is -4 right here. So we have our parabola, and then it's bounded above by z equals 2. So it's just like last time when we had the intersection between a paraboloid and a plane, we're going to end up getting a circle for this. Because if I set 2 equal to x squared plus y squared minus 4, 2 equals x squared plus y squared minus 4, then I could add 4 over here, and I have 6 is x squared plus y squared. So this time we're going to have a circle of radius √6 right here, and this is going to be our curve here. Okay, now this part's a little bit tricky. So let's imagine that so here's the normal vector kind of at the edge here. Let's imagine that we're a person like this, right? So we're kind of upside down, from our perspective at least, on this paraboloid. And if we're walking in a direction where the surface will be to our left, we actually have to go this way. So this time, since we're upside down compared to the way we were last time, right here, we're actually going to have to parameterize our curve clockwise in order for it to be positively oriented. Another way you could do this is you could literally flip the page upside down, and then we have the same situation as last time if we go counterclockwise, but upside down. So it might be easier to see it this way, right here. If it was a full sphere, it would have no boundary. Yeah, we wouldn't have anything to parameterize, and our surface integral would just end up being 0 right here. But anyways, we have this clockwise circle. All right, so this time we have a circle of radius √6. So the way we do parameterize a circle counterclockwise is we do it the same as if we were to parameterize a circle clockwise. The only thing is we put a negative on the y. So we have √6 cosine theta and then -√6 sine of theta, and then z equals 2 at this intersection right here. All right. Let's see, would a cylinder have 2? That's right, yeah. So an open cylinder where you kind of stopped it somewhere, yeah, that would have 2 different curves. Let's see. Are we only parameterizing the boundary curve? Yeah, that's right. Did nothing change? No, notice that there's a negative sign here. Now, why does this work? Why can't we just put a negative sign and it'll go the opposite way? Well, remember that cosine is an even function, right? So this is cosine of negative theta, and sine is an odd function. So this is sine of negative theta. And when we have negative theta, this means that we go around the opposite way. So we're spinning normally with just a regular theta, we go counterclockwise, but with a negative theta, we will end up going clockwise right here. So with this, we can simplify it. Cosine always eats the negative sign because it's an even function, and sine spits out the negative sign because it's an odd function. So that's where this comes from right here. It's just kind of a nicer version of this right here. All right, all we're doing here is boundary curves. Yeah, so all we needed to do is find the parameterization of the boundary curve for these problems. Okay, but that's about to change with the next problem here. Now we're actually going to use Stokes' theorem, or rather we're going to verify Stokes' theorem. So we're going to verify Stokes' theorem for this kind of interesting looking vector field. F is xxx, where S is the part of the surface, Z is 9 minus x squared minus y squared above the plane Z equals 5 with an orientation such that the Z component of the unit normal vector N is positive. And that kind of makes sense, right? If we draw our normal vectors, we want them to look like this here. So this is our surface. We have the paraboloid coming down, and then it's kind of stopped at Z equals 5. So this is kind of just like we practiced on the previous page right here. All right, so this is our surface. So what does it mean to verify Stokes' theorem? Well, Stokes' theorem was an equation, right? It said that this equation was going to be true provided we satisfy all of this, which we do. So what we want to do is we want to compute this integral, the curl of f dot n hat, and we want to compute this integral, f dot dr. And we want to see that they're the same thing because Stokes' theorem says that they will be the same. So we're going to compute each of these separately and then confirm that they're going to give the same answer right here. All right, so why don't we do the curl part first? You know what, let me, I actually have a blank piece of paper that I didn't use. So we could do this one fresh if we want. So this. Okay, so let me redraw the picture. Okay, do. There we go. Upward pointing normal vectors. That. All right, so first we want to compute the curl of f dot n hat ds. All right, so let's see here. So first of all, let's figure out what the curl of f is. So we got some practice doing this last time. The curl of f is the del operator crossed with our vector field. So what does that look like? Well, we set up our cross product. We have I, j, and k. We have the x derivative here, the y derivative here, and then the z derivative here. All right, and then our vector field is actually just x, x, and x. All right, so what do we get for this curl here? Let's see, for the I component, we do the y derivative of x minus the z derivative of x. Well, both of those are 0. Then we have the x derivative of x, which is 1 minus 0 for this. But then we negate it because it's j, so we have -1. And then finally for k, we have the x derivative of x minus the y derivative of x. That will yield +1 right here. All right, so this is our curl of f, which is nice and simple here. And then we want to figure out what we're going to dot it with. So we need to come up with some kind of parameterization of this surface, right? Because we're doing a surface integral. Now, the good news is that they gave this surface z as a function of x and y. Remember, this surface right here is z is 9 minus x squared minus y squared. So if we want to come up with a normal vector for that, it's always going to be negative gx, negative gy, and 1, where this is g of xy. Okay, so let's take the negative x derivative of this. So the x derivative is negative 2x right here, but then we get rid of the negative. The same thing happens for this y, and then we have a 1. And remember, we always need to check to make sure the orientation of our normal vector is right, but we know that the orientation of this normal vector is right because it's all facing positively for z, and that's what they wanted, the z component to be positive right here. All right, so we have both of our ingredients, so let's go ahead and do our integral here. So we have our integral. And then we're going to do the curl, which is 0, -1, 1, dotted with our normal vector, 2x, 2y, and 1. And then I guess we'll do dy dx. Now, what are we integrating over here? Well, we're integrating over this circle. And what circle is that? Well, it's where 9 minus x squared minus y squared equals 5, kind of like how we did in the previous examples here. All right. So then we're going to add x squared plus y squared over here, and then we're going to subtract 5 right here. So we have 4 is x squared plus y squared. Let's see here. So we have a question about the normal vector with n hat here. You could always just remember when we do a surface integral, you could always end up just using you could always just use this for a parameterization of if you have z as a function of x and y. So we could just use this. It doesn't necessarily need to be n hat here. All right, so we're going to dot this. Now we're integrating over the circle, x squared plus y squared is 4. So this is our region here. All right. Does the magnitude cross out? Yeah, I think we saw that when we first defined surface integrals with the RU cross R theta, that ended up canceling out because there's an RU cross R theta kind of hidden in this ds right here. So that, long story short, that proof we did maybe 2 classes ago is why we could just use the regular normal vector here, R theta cross, or RU cross RV, as opposed to having to find a normal vector. Will we have to check the orientation normally? Yeah, we need to make sure it's going in the direction that they specify here. But since we have a positive z component, we know that's going to work here. Where did the 5 come from? It came from the problem, z equals 5 right here. All right. How would we do it? You mean, what would we do if it, like this was negative? We would just multiply everything by -1. If this were like -1, for example, but we want it to be positive, then we would just multiply this by -1. That'd be how we would do it. All right, now we're integrating over a circle, right? So I don't really want to use x's and y's for that, although let's see what our xy integral would be. All right, we're going to have -2y and then 1. So we have 1 minus 2y dy dx right here. All right, but we're integrating over to circle, so that means we should probably use polar coordinates instead of rectangular coordinates. All right, so I'm going to flip this to polar. So I have 1 minus 2r sine of theta, r dr d theta. This is a circle of radius 2, so this will go from 0 to 2. And then theta will go from 0 to 2 pi right here. All right. So let's see here. So this simplifies to r minus 2r squared sine of theta. And if I do the r integral of that, we're going to have r squared over 2 minus 2r cubed over 3 sine of theta from 0 to 2. All right, let's do this real quick. We plug 2 in here, and we get 2. We plug 2 in here and get 16/3. All right, and then we do this integral right here. So we end up with 2 theta plus 16/3 cosine of theta from 0 to 2 pi right here. All right, so I plug in 2 pi and I have 4 pi. I plug in 2 pi here and I have 16/3. But then I plug in 0 and get 0, and then I plug in 0 here and get 16/3. But recall that this is the bottom bound. So we're actually subtracting. So those cancel out, and we end up with 4 pi. So 4 pi is going to be our surface integral right here. Now that's just 1/2 of Stokes' theorem, right? So this was the curl, or the double integral end of Stokes' theorem. What we want to do now is we want to do the line integral around the boundary of f dot dr. And we're going to see if that ends up being 4 pi. And fingers crossed, hopefully it should be if Stokes' theorem is correct. All right, so let's go ahead and do that now. So now we're doing the integral around the boundary of our surface of f dot dr. Okay, so let's look at our picture here. We need to come up with a parameterization for this circle. And what was this circle? It was 4 equals x squared plus y squared. All right, let's do this, r of theta. Now let's see, so we need to check the orientation here. So our normal vector on the edge will look something like this, right? So if we're a person that's the same size as this little arrow in the same direction, and we're trying to keep the surface on our left, we're going to end up going counterclockwise around here. So we're going to have 2 cosine of theta, 2 sine of theta, and then this happened at z equals 5. Which one will take longer between the curl integral and this integral? It depends on the situation, but it's nice to have the flexibility to do either one or the other if one ends up being really hard. That's the value of Stokes' theorem. All right, so let's remember how we did these line integrals here. So I'm doing this with the parameter theta, and theta will go from 0 to 2 pi to go all the way around the circle. So we're going to have the integral from 0 to 2 pi. We have f. Now remember what f was. F was x, right? So in this case, in terms of our parameterization, it'll be 2 cosine theta, 2 cosine theta, 2 cosine theta, like that. That's our x. And then we're dotting this with r prime of theta. So this was f. And we're dotting it with r prime of theta. That's how we do these line integrals. R prime of theta is -2 sine of theta, 2 cosine theta, and 0 right here. So that's what we're dotting with. All right, so let's go ahead and do this dot product, and then hopefully we'll end up getting 4 pi after we do the integral. Can I explain why it's x? Yeah, that's because that was the vector field that was given for the problem right here. So that was our particular vector field this time. All right, so we have 0 to 2 pi. We have this times this, so it's -4 cosine theta sine theta. We have this times this, so it's +4 cosine squared of theta. And then we have this times this, which is 0. Okay, so let's go ahead and integrate this. I think we're going to need to do some trig identities right here. So let's see here. What's maybe a better way that I could write -4 cosine theta sine theta? What's probably a better way that I could write this? -2 sine of 2 theta. Absolutely. So we're going to use the double angle identity for sine right here. And then for this, we're going to use the opposing identity, the half angle identity. So we're going to have 4 times 1/2, which is 2, and then plus 4 times 1/2 cosine of 2 theta. So this is what we're going to integrate here. All right. So then we go ahead and do so. If we integrate this, we have cosine of 2 theta. We integrate this, we have 2 theta. And then we integrate this, and we're going to have sine of 2 theta. That goes from 0 to 2 pi right here. All right, we plug in 2 pi for this. We have cosine of 4 pi is 1. We have 2 times 2 pi is 4 pi. Okay, that's promising. We see the 4 pi in there. We have 2 pi here. Sine of 4 pi is 0. Then we subtract. We plug 0 in here. Cosine of 0 is 1, so we're subtracting 1. And then we have 0 for this and 0 for this. And lo and behold, it turns out that Stokes' theorem works in this particular instance right here. All right, so we got 4 pi for both of these, verifying that at least Stokes' theorem works in this particular case. Now, we're definitely not going to go over a proof of Stokes' theorem like in full generality or anything like that, but we can at least see that it works in this particular instance here. All right, let's go on to our next problem here. Let me do it like this. Where did the 2's go? We divided by 2 when we integrated right here. All right, use Stokes' theorem to evaluate the integral of f dot dr. Okay, so that probably means that this integral is hard, but the double integral of the curl will be easier, where f is x, y, and then x, y, z. And the curve C is the triangle with vertices 1, 0, 0, 0, 2, 0, and 0, 0, 2, oriented counterclockwise from above. All right, so as you can see here, I already wrote this earlier, so let me just write over my writing. So we're using Stokes' theorem here. So we're relying on the fact that the integral of f dot dr, what we have to compute, is the same thing as the surface integral of the curl of f dot n hat. So this should be a hat. Made a mistake earlier. Yeah, so again, let me address this right here. N hat ds is the same thing as n that doesn't have to be a unit vector dA right here. So once we actually switch into our parameters right here, then we could just use n, which was RU cross RV, which depends on our parameterization. So we don't have to make it into a unit vector to do this. Okay. So let's see here. All right, well, we're supposed to compute the double integral of the curl. Well, let's compute what the curl is right here. Why do we have a C and not an S? You mean right here? The curve C is going to be the boundary of this. So going along the edge of this triangle is C. C is the boundary of the triangle, going counterclockwise. And then S is the surface. So if we fill in this triangle, that will be S. All right, let's compute our curl. The curl of F is del cross F right here. So we are going to do our determinant, I hat, j hat, and k hat. We have partial x, and then we have the y derivative, and we have the z derivative. Okay, and then we put in our vector field, which is x, y, and then x, y, z. Okay, this one should be a little bit more complicated of a curl than before. If we compute the I or the x component, we have the y derivative of x, y, z, which is xz, and then we have the z derivative of y, which is 0. So we have xz for our first component. For our next component, we're going to have the x derivative of x, y, z, which is yz, and then we subtract the z derivative of x, which is 0, and then we put a negative on the whole thing because of j. That's probably like the easiest negative to forget about in math. And then k right here, we do the x derivative of y minus the y derivative of x, but those are both going to be 0. Okay, so there is our curl right here. All right, so next what we want to do is we want to get our normal vector. Now what we're going to do is we're going to come up with an equation of the plane right here. So we want a plane that includes the point 1, 0, 0, 0, 2, 0, and 0, 0, 2 right here. So what I did was I made up this plane. It's going to be 2x plus y plus z equals 2. So this is going to be the plane that includes all 3 of these points right here. You might be wondering, okay, how did I just come up with that magically? What I did was, so I looked at the least common multiple of all these numbers, which is 2. And then I did that divided by whatever the number is here and put it next to the variable. So I did 2 over 1 is 2 times the x, 2 over 2 is 1 times the y, and 2 over 2 is z, which 2 over 2 is 1, because the next is z here. And then we put the least common multiple number over on this side. And that will give us our plane. Now, because we have such a relatively simple formula for our surface, we can solve this for z. So I'm going to subtract 2x and y over. So z is 2 minus, or let me write it. Z is 2 minus 2x minus y. And that's good news because we know how to find the normal vector, or RU cross RV, with something parameterized as x and y, and we end up having a z. So our normal vector, remember, it's going to be the negative x derivative of this. So the x derivative is -2, so we get rid of the negative. Then we have the negative y derivative of this right here. So we take the derivative of this, have -1, and then we negate it. We have 1. And then we always have 1 for that component over here. And let's see here. We want to make sure this is oriented counterclockwise from above. So we want to make sure that we're not going to use the negative of this. But if you draw this vector 2, 1, 1 that's coming out, it's kind of hard to draw. It's coming almost directly at us. So maybe I'll draw like this. This is kind of popping out of the triangle. And if we follow this curve, that normal vector will be on our left. So this is an okay normal vector to use. Why is it 2x? You do the least common multiple of these 3 numbers here, and then you do that number divided by this, and that'll be your coefficient. So we have the least common multiple of these is 2, and then we divide by this, which is 1. So we get 2x. All right. How do we know to go around and counterclockwise? Because it says it right here. Yeah, so these problems have a lot of information to keep track of here. Can I explain how to know if it's oriented in the right direction? You kind of just have to try to visualize it here. So let me draw this again. So here's our triangle, right? The normal vector is kind of popping out of it like this, so kind of coming out of the page towards us. And if we travel around counterclockwise, and we go in the same direction as our normal vector, then our surface will be on the left. If we imagine that we are the normal vector and we're walking around this path, oops, like that, then our surface will be on our left here. All right. So now we have our normal vector, we have our curl, so let's set up our integral. Now this is not going to be an integral that I'm going to do all the way through, and you'll see why. Okay, so this will be the double integral of 0 to 1 and 0 to 2 minus 2x, and I'll explain how I get that in a second. And then we have our curl right here, dotted with our normal vector right here, dy dx. Okay. All right, so I do the dot product and I get this. Now, how do I, or let me write it. I want to make sure people have time to write it. 2xz minus yz dy dx. All right, now let me explain how I got the 2 minus 2x bound right here. So if we look at how this works in the z equals 0 or the xy plane, if we plug in z equals 0 to this to see what our x and y bounds will be, we end up with 2 equals, or no, we should do, if we put 0 here and we add y over, we end up with y is 2 minus 2x. So that's going to be kind of this bottom edge of the triangle here. And then our other edge for y will be 0. So this is kind of how we normally set up double integrals here. All right, so this will be 0 to 2 minus 2x, and then this is 0 to 1. Now we can't have z in here. We can't have 3 variables if we're only integrating in respect to 2. But thankfully, we know that z is 2 minus 2x minus y. So I'm going to factor out a z from this. So that's 2x minus y. And then I'm going to substitute z in here. So that's 2 minus 2x minus y right here. Now, I'm not going to do the rest of this. And I tried to do the rest of it earlier. And it ends up just being polynomial mania, essentially. Like you end up getting down to this. And maybe you could do some clever use substitution and do this a bit faster. But in all likelihood, you're probably going to have to FOIL all that out and to do a bunch of power rules and everything. So I just said it was a grind. It turns out this integral is actually just 0. So it'd be immensely disappointing to do all of this work with all these polynomials and then just get 0 out of this. I don't think there's any special reason why this is going to be 0. I think it's coincidentally going to be 0. I don't think there's anything to be gleaned from this. I think it's just coincidentally this polynomial integral will end up being 0 right here. All right, yeah, so we can't tell if like f is conservative or anything like that. Well, actually, we know f isn't conservative because the curl of a conservative vector field is 0. But yeah, we can't tell anything special from that. All right, so I'm just going to cover that part up because we don't really need to look at that. All right, and then finally here, we're doing on time. Oh, geez. All right, use Stokes' theorem to evaluate the double integral of the curl dot n hat, where our vector field is negative y, x, and 0, and S is the tilted disk enclosed by this curve right here. So they were kind enough to give us a parameterization right off the bat here. Oriented so that the z component of the unit normal vector n hat is positive. So we want a positive z happening again. All right, so let's see here. So what did I do for this one? Well, what I did was I wanted to see exactly what this disk looked like. So what I did was I plugged in a few different values for t. So I plugged in 0, I got 1, 0, root 3 from that. That ended up being this point right here. I plugged in r pi over 2, which will then be 0, 2, 0. That's going to be this point right here. All right, so we kind of curve over like that. There's our arrow. I'm bad at drawing these arrows. There we go. All right, if we go to r of pi, this is going to be negative 1, 0, negative root 3. That's going to be down here. So we're going to come from here and then curve down towards this. And then finally, or not quite finally, we have r of 3 pi over 2 is 0, negative 2, 0. So from down here, we're going to curve up to this, which is 0, negative 2, 0. And then anybody, I bet you can guess what happens with r of 2 pi right here. We're just going to come back around to where we started. So this is going to be our tilted disk. Now, it's very hard to visualize what this looks like kind of in this 2D projection right here. The way to imagine this is that this disk leans back in the x direction. So this disk is kind of going out diagonally this way in the x direction right here. So it's kind of leaning back this way. It's slanted a little bit. All right, now why did we need to do that? Well, we needed to know that this is oriented positively. Now, if I draw a positive, or if I draw a vector with the z component of the unit normal vector is positive, that'll kind of pop out like this. So if this is kind of my flat surface, my z vector will be popping out like this, and it will actually be positive. So the way that I'm drawing around this curve actually is going to be the correct orientation here. So I don't need to go in the opposite order of this right here. This is really hard to see, so don't feel bad if you're not able to quite see this. But the moral of the story is that we don't need to do this in the negative t direction like we did for that problem earlier. We could just use it in the order it's given. All right, now we're going to use Stokes' theorem. So rather than doing this curl, which may have been difficult, so rather than doing this surface integral here, we're instead going to go over the boundary of the surface, which is the circle. We have f dot dr. All right. Now earlier, way earlier before class, I computed what r prime was. R prime is negative sine of t to cosine of t, negative root 3 sine of t. All right, so there's our r prime. Now remember, that's how we do f dot dr right here. So we have f. Remember, our vector field was negative y, x, 0 right here. Is something going on? Did I miss something? Why is everyone doing these exclamation points? Isn't it on the right? No, all right. It's really hard to see this. This is pointing in the right direction. Maybe I should have gotten a computer algebra system for this. Let me try to draw it in a different way. Okay, so it's kind of leaning back in the x direction, right? Then the normal vector is popping out like this. So it's leaning back in the x direction. The normal vector is popping out to have a positive z component, and we're going around it like this right here. So it actually is in the correct orientation. I'm sorry, this picture is awful. It doesn't let you know what's going on. It's really hard to visualize this, but this, trust me, this is positively oriented. All right. So I'm just going to speed through this real quick. This isn't a difficult integral or anything. So we have -2 sine of t cosine of t. If we plug our parameterization into our vector field here, and then we have r prime. Yeah, this, to be honest with you, this one you might just want to flip a coin. It's really hard to see this. I wouldn't blame you if you did something like that for this problem. All right, so, and then I do the dot product and I get this integral right here. And we know what this is. This is going to be 2. And the integral of 2 from 0 to 2 pi is 4 pi, which I think was the answer for one of the other problems as well. All right, so there we go. So in this case, doing this was way easier than doing the curl here, or at least I think so. Maybe the curl of this won't be too bad, but it might be hard to find out what surface. Actually, yeah, this would be hard to write down the x and y coordinates of this surface. That'd be kind of rough. So we definitely want to use Stokes theorem here. All right, so let's see here. Let's move on to lesson 34 with our few minutes left right here. I want to at least get started with this. So in this lesson 33, we talked about something called the curl, which is the del cross f. So it's that gradient vector with all the partial derivatives crossed with f. Now, one thing you might be wondering is that, okay, well, that's the cross product. But remember, we have 2 different ways of multiplying vectors together, right? We could also use the dot product. So what happens if we dot the del vector with f? And this is going to be called the divergence. So this is sort of the other side of the coin of curl right here. So the divergence of a vector field f is PQR, where the component function is differentiable, is going to be the del vector dotted with f. So what does that end up being? Well, we have partial x, partial y, partial z dotted with p, q, and r right here. So we do the x derivative of p, and then because of dot product, we add the y derivative of q, and then we do the z derivative of r. So the nice thing about divergence is it's way easier to compute than curl. We just do the matching derivative to what component we're in here. It's very easy, and then we add them together. Now, unlike the curl, one thing I really want to note here, well, actually, they note it right here. Note that the divergence of a vector field is a scalar valued function. I didn't draw any brackets around this. There aren't any commas here. This is just a scalar function. And that makes sense, right? Because we're doing the dot product here. And remember, the dot product, way back when we were first learning vectors, those were just numbers. Those were just scalar values. So it's going to be the same thing here. We get a scalar out of doing the divergence here. And I haven't seen this term too often, but I think it's worth knowing here. If the divergence is 0, and notice this is 0 without the little vector because it's just a number, then f is called incompressible or source free. I kind of like this term better, and I'll explain why in a minute. Okay. All right. So let's see. Oh, and then I guess I jumped the gun on this. I was supposed to show this end up being px plus qy plus rz down here, but we already just saw that. So I'm not going to write that in. So yeah, so the divergence, we just take the matching derivative of each of the coordinate functions for our vector field. Okay, now this is, so kind of like how the curl kind of deserved its name. It was roughly telling you how much you were twisting around a particular axis. Divergence also makes sense if you think about the physical interpretation. For a physical interpretation of divergence, we could think of the divergence of a vector field at a point is the net flux of the vector field per unit volume through a small sphere surrounding the point. Okay, so that's a technical way of thinking about it. The kind of the layman's terms way of thinking about it is it's how much the vector field is radiating away from a particular point. So for example, if we have a point here and the vectors look like this, then this would be a high divergence point because we're kind of radiating away from this point. If we have a point and then all the vectors are kind of coming in, this would be a large divergence value, but it would be negative. And then if you have a point and it seems like we're not really going towards or away, then that would be a small or close to zero divergence right here. So loosely speaking, it's how much the vector field is radiating away from a particular point. All right, so let's kind of put this intuition to test here. Let's say we have this vector field F, and it's shown in this picture right here. I guess I already gave the answers on my page, but determine the sign of divergence of F at points P1 and P2. All right, now let's take a look at P2. So P2 is right here. Remember, we're drawing a small little sphere, or since we're in 2D, I guess it's going to be a circle around our point, right? We have this. Now, on the face of it, it seems like this divergence might be zero because we have vectors coming in this way, but then they're also coming out this way. So the positive and negative parts might seem like they're balancing out. But one thing we notice is that the vectors here in the back are bigger than the vectors here in the front. So even though they're all going the same way, the ones coming into the circle will overwhelm the ones going out of the circle. So that's why the divergence at point P2 will end up being negative right here. All right, and then with P1, we sort of have the opposite phenomenon happening here. So let's draw a little circle around P1. So here we have kind of smaller arrows coming in like this. So these little small arrows, and then we have the bigger vectors coming out. So it seems like even though we have some vectors coming in, some coming out, it seems like the ones going out are longer or bigger than the ones coming in. So since we have more stuff going out, P1 is going to have positive divergence. Now, can you guys tell me a place on here where we would maybe have zero divergence? Does anyone see a place like that? That's right, the origin. Because actually at the origin, it looks like we just have the zero vector right here. So there are just no arrows, period. So yeah, there'd be zero divergence right here. But also there would be zero divergence at other places as well. Like for example, along this axis here, if we looked at this point, this would also have zero divergence because the arrows coming in are the same size as the arrows going out. So it's going to be zero divergence along these axes as well. But yeah, also at the origin right here. All right, I think we should have just enough time to take a look at the next page here. Okay, so let's talk about, so this has to do with flux, right? So it seems like divergence has a strong relationship with flux, or how much arrows come in and out of a certain region. So this is going to enable us to get a different version of Green's theorem. So suppose D is a region for which Green's theorem holds, meaning it's like the simply connected, all of the kind of things like that. And the boundary of D is a positively oriented boundary in the way we discussed in the previous lesson. If F is P and Q, so we're back to a two-dimensional vector field, and it's a twice continuously differentiable vector field on D, then if we do F dot N ds, this is going to be the double integral of the divergence dA right here. Okay, so let's see why this is. This seems a little bit weird. So here's our picture. So here's our curve, and I'm guessing we have the boundary or the actual surface over here. And then here's n hat. So what is this guy measuring right here? This is measuring how much the vector field is perpendicular to our path. So the more perpendicular our vector field is to our path, or the more the arrows are kind of coming out, the bigger value that this is going to be. All right, so that's what this is measuring here if we do F dot n hat. All right, now let's start here. Let's start with on this side of the equation. We have F dot n hat, right? Okay, now our vector field F was defined to be PQ right here. So that we're just putting in what F is, it's component P and Q. Now, this is the strange part. So what we're doing is we're going to rotate our picture 90 degrees. So rather than kind of orienting ourselves this way, we're instead going to orient ourselves along the tangent vector right here, t hat. We're instead going to look at things this way. Now, so what we're doing is we're rotating this 90 degrees, rotating n hat 90 degrees is going to give you t hat. But in order to keep things consistent, we also need to rotate our vector field by 90 degrees as well. Because if we did that to this, we also need to do it to this as well. Now, remember way back when in the vector section, I told you guys a kind of a quick way to find an orthogonal vector or a vector that's rotated 90 degrees. You switch the components and then you negate one of them. And that's exactly what happened here. We flipped P and Q, and then we negated Q. So PQ is going to be perpendicular or 90 degrees away from negative QP. So we're effectively computing the same thing. We're kind of just doing it in a different way. We're looking in the t hat direction, and instead of looking at the actual vector field, we're looking at the vector field rotated 90 degrees. So this is kind of the weird step right here. Okay, now this dotting with t hat, I don't know if you guys remember this or not, but this is how the original Green's theorem worked. Because original Green's theorem wasn't talking about going out this way. It was talking about moving along in the direction of the curve right here. Why are we doing that? You'll see in a second. So according to regular Green's theorem, if we have the integral of a vector field dot t hat, then we could use Green's theorem on that. So we do the x derivative of our y component. Wait a minute. Yeah, we do the extra, I don't know, I must have made a mistake earlier. Yeah, so we do the x derivative of our y component, and then we subtract the y derivative of our x component. So this is our new x component, right? So we're going to subtract the y derivative of that. So this is due to the original Green's theorem. Now, if we look at this, we did the negative of this negative here, so we're going to end up with a positive. So we end up with, and then this is wrong, this should be q sub y and then p sub x. I don't know what I was thinking earlier. All right. And then what do we have here? Well, if we look at del dot f, remember this is the x derivative of the x component plus the y derivative of the y component. So this is none other than del dot f, or the divergence here. All right. I know this part was a little bit confusing with the perpendicular thing. This is essentially just kind of a basic justification of this formula up here. Yeah, so that's kind of a basic justification of what's happening up here. So this is going to allow us to compute flux in two different ways. So kind of like how we use Stokes' theorem to compute line integrals of the surface integral of curl in two different ways there, and we switch to the easier one when possible, we're going to do the same thing with this right here and the divergence of that. All right, so then for our final class, all right, so we're done now. So our final class, what we're going to do is we're going to practice doing this. We're going to see that this also works with 3 variables right here. So it works pretty much the same way. And then we're going to cap it all off with something called the divergence theorem. And then I could summarize everything we learned in the class. Because some people have been saying that all of this stuff kind of seems vaguely the same. Maybe just like kind of tweaking it each time. And you're not wrong with that. These are different manifestations of the same thing. And we'll see how all that works tomorrow. So I will see you guys